slide reminds us, so you still have time to get your pumpkins and candy, George Santos costume, whatever. It's 14 days only to get your votes in before Election Day. It's 37 days till Thanksgiving, and believe it or not, it's only 70 shopping days left until Christmas. But with that, that new Costco, it's only 4 roundabouts away, and so after you do all your shopping that you possibly can here at Sisters, you head down there. And just word to the wise, if you do head to Bend, make sure to check the maps so that you don't get diverted to Redmond on the way home, if anybody's down there that late. But before we get started, a couple things. Thank yous, as we always do, to first and foremost the impresaria of Sisters, our friend Angeline, our hostess for this evening, who is always so kind to us for this. We have a number of our board members are here tonight. I'm just going to read off all their names, even if they're not here, but David Duran, Don Utzinger, Gail Todd, Larry Price, David Ellis, Dave Johnson, Jocelyn Blevins, Joe Sherry. These people meet 5 nights a week for up to 6 hours per meeting to arrange them. So let's give them a hand too. Yeah. Karen Schweigert and Ann Richardson, I think we probably greeted you at the door. Thanks for coming, you two. David Duran and David Ellis set the chairs and tables the way you see them tonight. Peyton Myrie earned his keep he's running AV tonight, and without him, we wouldn't have had slides. So thank you, Peyton, for putting it on fire. I mentioned that our next speaker is only 28 days from now, and that is the 3rd Tuesday. We're normally the 4th Tuesday, but Aaron Bott, this is one that we've announced a few months ago, is a wildlife biologist with Oregon Department of Fish and Wildlife. And the talk sounds super interesting to me. He's titled it Wolves, a Social and Natural History. And I think that's going to be a topic of interest to all of us. December we're skipping due to, I think, their holidays. And then in January we have a new one to announce. Dr. Jamie Cornelius from the OSU Department of Integrative Biology is giving a talk this sounds interesting. Amazing adaptations. Can birds reduce the stress of climate change? Let's all hope the answer is yes. Because, so we'll see. We'll learn more about that one in 3 months. A couple things. The goal of these Frontiers of Science lectures is just to give our little community here in Sisters an opportunity to hear from, and if those of you choose to, interact with a broad range of people that are working at the frontiers of science. In recent talks, we've hosted distinguished practitioners, professors, lecturers from across the Northwest and beyond in biology, in medicine, ecology, geology, health sciences, and the most fundamental of all science, physics. Does everyone here love physics? Yes. And this is an audience that you can feel comfortable saying that in, so thank you. For those of you who attend these talks regularly, another thing that I really enjoy attending them regularly myself is that we find ourselves among others who care about science enough to come out here and spend the time. And people who are humbled by the boundless creativity that we can find in nature all around us. People who are themselves committed to learning and who often are the same people who are committed to ensuring that we have robust science curriculum in our local schools. Yay. Thank you. Some of our teachers are here tonight. And I also believe that the rules and realities that we humans can puzzle out through scientific research and collaboration have to mean more than public relation talking points when it comes to informing public policy. So I really appreciate that you're all here tonight to participate, at least as an audience member tonight, in science and science education. So thank you for coming, and bring your friends next time. Beyond the fielding an audience, however, Sisters has a couple other tricks up their sleeve, and I think we're going to hear from one tonight. in our little town, in our audience on a regular basis, and actually on the Science Club board itself, we happen to have such a distinguished practitioner, truly a leader in his field, who's done important work of international significance over a long career, and he's going to be presenting to us in a few minutes. Larry is a brave man. Our speaker tonight has taken on the challenge of helping those of us in the audience understand the underpinnings of quantum mechanics, which is possibly, the most accepted and least understood pillar of modern science. And no less than Richard Feynman, who I'm sure you're all familiar with. He's one of the most celebrated American scientists in any field of all time. A pioneer, a major contributor to the field of quantum mechanics, has a Nobel Prize for quantum electromechanics, a subfield. Came up with the path integral approach that we call the Feynman approach. And he was quoted once as saying, "I think I can safely say that nobody really understands quantum mechanics." And in that, he was including himself. And of course, he was a colorful lecturer. And so in a different context, on a different day, he also said, "What one fool can understand, another can also." So, and yet a different occasion, he also said, "The first principle is that you must not fool yourself, but you are the easiest person to fool." So our speaker has set himself a big challenge, which is, I think, helping us all fool ourselves that we know something about quantum mechanics by the time we leave tonight. Dr. Larry Price is a distinguished physicist in his own right. He is specialized in elementary particles through his career. Larry holds degrees in physics from Pomona College, where he earned his BA, and from Harvard University, where he got both his master's and PhD. He was a senior physicist and the director of the High Energy Physics Division at Argonne National Labs in Illinois for a number of years. And in part, I think, with your Argonne hat on, Larry was a team leader at the Atlas detector at the Large Hadron Collider, which is that, in the CERN project, incredibly large and complex project that found the definitive results for the Higgs boson a few years ago. Larry served on multiple national and international committees for particle physics and related fields, including the High Energy Physics Advisory Panel, the U.S. Federal Advisory Committee for Elementary Particle Physics. And I think from talking to Larry before, the real feather in his cap is that he is a board member of the Sister Science Club. Recently elected. And I'm just going to do one quick thing before I invite Larry to take the microphone on the stage. They do say that experiment is king. And I know that there's something that has to do with quantum mechanics and a black box and a cat. So I don't know where Martha is, but with Martha's help, earlier tonight I dropped by Larry's house and I picked up his beloved Minxie the cat. And although I don't have a black box, I'm just going to put it right over here. And perhaps after, let me just show you. So at the end of the evening, if perhaps after Larry's talk and a little bit of Q&A, Larry, while the cat is superposed right now, Larry can explain to us or reveal its true quantum state. So with that, I invite to the stage Dr. Larry Price.
Well, good evening. It's great to be back at the Sister Science Club. It's always fun to talk here. And I kind of think that its big attraction for a lot of us is the social aspect. We get to come and talk to our friends who are interested in science, but also just a chance to chat. But it is also true that it's a group that is interested in science and amazingly, in a small town like Sisters, can get enthusiastic about science. And so it's great to be with you all again. Yeah, I'm not sure what whether I should try to sit down or just what. But, okay, so I should have known that. Is that too much? Yeah, but I don't want that arm in front of the screen. That's the problem. Okay, is that? No, I see. Ah, dear. So, Rob, could you just hold it while I talk?
I'll take it while you talk. Thanks.
I think I may have it, Rob. Yeah, no. Anyway, yes, for the moment it's not. Okay. Thank you, Rob, for the introduction, and I should have known that you would take all of my best lines. So I'm starting off with a quote from one Richard Feynman, and the main thing that I'll point out is that he said this in 1965, which was the year that he won the Nobel Prize as one of 3 physicists who got the Nobel Prize for giving a quantum version of electricity and magnetism called quantum electrodynamics, which has been the theory of electricity and magnetism ever since. Well-deserved Nobel Prize. But he said, as Rob just told us, I think I can safely say that nobody understands quantum mechanics. And not to give anything away, but in the, how long has it been? 59 years. Since then, nothing has changed. So this is just a warning if you thought I would explain quantum mechanics to you tonight. However, the place to start, and trying to start with a bang, with a big claim or a big statement. Nobody understands quantum mechanics. Let's take that as a given. And yet, quantum mechanics is accepted as the underlying mechanism for, and I put this in red, all phenomena in the universe. That's amazing. I trust you'll agree. So a few bullets. It gives incredibly precise results where it's able to calculate so precisely. And mostly that shows up in the area where Feynman did his work. So the calculation of the electron magnetic moment agrees with the 2022 experiment, the last time it was measured in detail, to 1 part in a trillion. And that, I'm an experimenter, I've never measured anything to 1 part in a trillion, or even within a factor of 1,000,000 of that. So it's incredible that both the calculation and the experiment can be done so precisely. And while it succeeds in that area, it has made calculations. Calculations have been made using quantum mechanics in many, many other fields. And it is not contradicted anywhere by any measurement. And that also is quite amazing. So that's about as close as you can get in my field to saying, therefore it must be true. We're not allowed to conclude that because the next experiment can always contradict it. But it seems pretty well established. The trouble is, as Einstein, for one, pointed out, it involves seemingly arbitrary rules to get those results. And I'll show you a little bit later just how arbitrary that is. And nobody understands how it works. And I'll quote Feynman. I'll refer to my quote on Feynman. So the double star footnote says that what is going on there, trying to understand it, has been an active field of research since the 1930s, only about maybe 5 years after quantum mechanics could be said to be established. And it still is an active field of research now. So although I say nobody understands it, there are some people on the cutting edge of trying to understand what's called the interpretation of quantum mechanics that think they do understand how it works. And maybe they're right, but we don't yet have a consensus that we can say across the field we all agree that this is what's really going on underneath. So those are the claims about quantum mechanics. It can calculate virtually every physical process in the universe, but it's like one of those cartoons that you see occasionally, or they dig up occasionally from the old days, where the guy at the blackboard, the mad scientist at the blackboard, says, and then a miracle occurs, and a big arrow, and and here's what comes out, and you have to accept it. Okay, so here's the way I'm going to try to organize what I'm saying here. So I'm going to try to indicate why in roughly 1900, before all the action got started, there didn't seem to be any need for something new. And in fact, there were people claiming that physics was basically completely understood. We know that's always dangerous to say. But there were storm clouds. And there were beginnings of indications which firmed up in the early part of the 20th century that indicated that things that were thought to be waves seemed to have particle-like behaviors. And eventually things that were thought to be particles eventually showed up with wave-like behaviors. So even though it seemed that physics was almost all understood, there were these niggling little things that I called storm clouds that eventually created a real storm. And it took quantum mechanics to sort of solve it or make the rain go away. And then I'll talk about de Broglie's hypothesis that everything is both a particle and a wave. So light, that we always thought was a wave, also has particle-like properties. An electron, that we always thought was a particle, has wave-like properties. And that became the gospel of quantum mechanics and led very quickly to what I call the master equation, the Schrödinger's equation, which is the new basic equation of the universe, replacing maybe Newton's F equals ma. So with quantum mechanics, as it began to be understood, were new phenomena that made it seem completely different from what had gone before. There was the role of the observer, and this was part of the magic that I alluded to, and I'll explain why that's so mysterious. There's the uncertainty principle that Heisenberg developed from his own incarnation of quantum mechanics that was based on matrices and less on waves, but still it turned out to be equivalent to Schrödinger's quantum mechanics based on waves. And then the spooky, what Einstein called spooky, phenomenon of entanglement. That two particles which may be halfway across the universe or all the way across the universe can still be entangled in such a way that a measurement on one of them tells you what's going to happen with a measurement on the other. I don't want to say it determines what happens with the other one, but it tells you what the answer is going to be. And then I'm going to sort of talk briefly about how quantum mechanics was extended to virtually all physical processes during the 20th century, during the last century. And a lot of work now is going on what's going on behind the curtain, why does it work, what is an interpretation that tells us what's really going on with all these mysterious things. And I probably won't be giving anything away if I told you that Feynman is still basically right, that nobody understands quantum mechanics. So that active research is still going on to say what's really going on. All right, so the need for quantum mechanics. At the turn of the 20th century, almost all of physics seemed to be well understood. And I'm not even, oh, that's for my water, great. Thank you very much. And I just mentioned a couple of things, and I'll mention a few more in a moment. But there were these gathering storm clouds And the reason really to go through this is that while there are maybe 4 things that could be called storm clouds, I'm only really going to go into 2 of them tonight, namely black body radiation and the photoelectric effect. And the others are important. Why is matter stable? That sounds like an important question, but I'm not really going to discuss it. And why do optical spectra from excited atoms show distinct lines rather than a continuous spectrum? And I'm not really going to go into that either. All right, where did we start out in 1900? Newton, we had, on the mechanics side, we had Newton's law, I quoted it, force is equal to mass times acceleration, and an interpretation of that is that if you know the whole state of the system in advance, if you know for every particle in the system, or for every object in the system, exactly where it is, and exactly how fast it's moving, or what its momentum is, if you apply F equals ma and you know what the forces are on each of those particles, you can predict the state of the system and exactly how much momentum each of those objects is going to have indefinitely far into the future. That's pretty good. I mean, how could you want more than that? We already had that in 1900. Importantly, and this was important to Newton, it was important to Einstein, the system is deterministic. If you know all these things, you can determine exactly what's going to happen going forward, and you could even run the equations backward and determine what would be the state of the system yesterday, or if it's the right kind of system 100 years ago. So it's deterministic. Once you have the state of the system, you can push it forward or backward, and you know exactly what it's going to be like then. F equals ma refers to the effect of forces on each of the objects. And Newton, of course, importantly told you how to calculate the force of gravity, the first line there. But as the field developed, other ways of calculating forces also came to be understood pretty quickly on the electrical end of things, and other aspects of electricity and magnetism, elastic forces such as you guessed with a spring, fluid forces, for instance, that keep airplanes up in the sky, and so on. So from the mechanical end of things, a lot was understood, or it seemed like it. From the optics point of view, light, a lot was understood. Everybody knew it was a wave. And there was this experiment that Thomas Young did in 1801, known as the double slit experiment. And if you come down from the top, you have sunlight impinging on this whole apparatus, a single slit that spreads the light out, and then onto a double slit. And I don't think I'm able to point, I was hoping I could, but as light goes through each of those 2 slits, you get new wave fronts showing up, and you get basically wave patterns such that in a certain direction, and for the red arrows go, for instance, the peaks and the troughs of the waves come together in the same place all along that red arrow. And so when you look at the end of the red arrow where there's actually an indication of what you would see if you look at the amount of light coming out, you would see a light fringe. You would see an area that was light. Where the black area goes, the peaks of the waves from one slit match up with the trough of a wave from the other slit. They cancel each other out. And so where the black area goes, arrow goes, you basically get no light, and it shows up black on the screen. And then going still from left to right, you get another red ray, or red direction, where the peaks line up with the peaks and the troughs line up with the troughs, and you get another bright spot. So that was a well-known demonstration of the wave nature of light. It was 100 years old in 1900 and well understood and well established. Other aspects of electricity and magnetism, Coulomb's law, the force between two charges, that was dated to 1785. And there's Coulomb looking appropriately 18th century in his dress. Ampere's law, 40 years later, roughly, forces produced by a magnetic field, and the magnetic field produced by an electrical current. Here's Ampere. It's not a question of whether color photography was invented yet or not. Color painting was, but he was looking at least appropriately 19th century. Faraday's law is going to the middle of the 18th century, of the 19th century. There's Mr. Faraday. He really produced the connection between electricity and magnetism. And finally, Maxwell, who put it all together in 1865 with his famous 4 equations that summarized all of electricity and magnetism. Okay, so that's the things that were understood, at least in brief. I've titled my next slide, ironically, Complacency in 1900. Albert Michelson, who among other things showed experimentally, essentially, that there is no luminiferous ether. All those waves, all those light waves, waves take a medium. You know, ocean waves work in the ocean and in the water. Waves on a rope, the rope is a medium, light. For light, there was no apparent medium, so they invented a medium that they called the ether, or the luminiferous ether. And Michelson, along with his colleague Morley, did an experiment that I won't try to go through in detail now, but he pretty definitively showed that there is no ether, or something funny is going on that wasn't understood at all. So he tried to measure the speed of light to the ether by setting up an apparatus that would either be going along with light to the ether or at right angles to the light to the ether, and it made no difference. He measured the same speed of light in both directions. He said that in 1894. He said, and I haven't read it, I'll read it briefly. While it's never safe to affirm that the future of physical science has no marvels in store, it seems probable that most of the grand underlying principles have been firmly established, and that further advances are to be sought chiefly in the rigorous application of those principles to all the phenomena. And I'm going to skip down here, and where he quotes an eminent physicist recently remarked that the future truths of physical science are to be looked for in the 6th place of decimals. So I never saw any follow-up on what he thought of that some years later, but he must have been a little chagrined. So very briefly, a couple of storm clouds, black body radiation. The measurements of black body radiation date from the work of Pierre Provost in 1791, a physicist that I've actually never heard of before I started putting this talk together. But a number of leading physicists of the day worked hard to try to predict the results that Prevost got it, and other people got as time went on. So a black body is the perfect radiator, and it radiates a reproducible spectrum that depends on how hot it is. So if it's down here at 3,000 degrees Kelvin, Kelvin is the temperature scale starting from the lowest temperature you can get to, absolute zero. And it's a spectrum that tends to look orange. You can see where the line goes relative to the visible spectrum. Most of it actually, it peaks actually well away from the visible spectrum, but it's got a reasonable amount of energy in the red-yellow part of the spectrum, and it shows up orange. And in fact, 3,000 Kelvin is just about the temperature of the surface of the sun. So that orange that we see out there is black body radiation. Funny to call it that, but at 3,000 K. When you get to 4,000 K, the spectrum peaks earlier, and it's emphasizing more the middle of the spectrum, so it shows up rather green. 5,000 Kelvin emphasizes at least the middle of the spectrum, and it tends to show up bluish. Now, you take classical physics, and you go to try to calculate these spectra, what actually happens as a function of wavelength. That's the horizontal axis here. And it does, well, not too badly, maybe trying to calculate for 5,000 K, which is this blue line. But it starts rising as the wavelength gets shorter and shorter. But the trouble is, it never stops rising. And it quickly gets, not quickly, but it eventually ends up in infinity, which is really a no-no for physicists. We really don't like things that show up in infinity because that's a number that's very hard to measure and is almost surely wrong. So they knew it was wrong, Rayleigh and James, who did this calculation. And so over the course of the 19th century, many other people tried to calculate. They did more or less, they hit it more or less right, not more or less right, but came closer or farther away, but nobody really did it, and it was known that classical physics was not giving a calculation of black body radiation, which was a pretty fundamental part of physics, that was at all satisfactory. It was some of the latest people here, Rayleigh and James, actually did their work between 1900 and 1905, and they were the people that produced this black curve that was heading to infinity, at much too large a wavelength. So, not too encouraging. Planck, in 1900, so the work of Rayleigh and James actually overlapped the work of Planck. He actually came up with a formula that actually matched the spectrum of black body radiation at whatever temperature. And I'm not going to go through the details of the formula, but he did it by introducing a new constant that he called h. And it's now known as Planck's constant. It's a very small number, 6.6 by 10 to the 34th, and you understand the notation, 10 to the minus 34th. 10 to the minus 34th is a decimal point, and then 34 zeros and a 1. It's a very, very small number, but it was appropriate for dealing with the atomic scale. It's a new addition to the constants of nature. It's lasted ever since. And it gets used in this formula along with the speed of light. Boltzmann constant, which has to do with thermodynamics, also a rather small number. And the point of this constant is that he made the assumption that the emission of energy, of light or other types of electromagnetic radiation, comes not continuously, but in what began to be called quanta, and therefore eventually quantum mechanics, such that Planck's constant times the frequency was the amount of energy emitted in a packet, in a piece. It could also be written as Planck's constant h times the speed of light divided by the wavelength. And so, why did he make that assumption? Well, it was initially a calculational tool because he couldn't do the calculation otherwise. It tended to give infinity. And this is often, this kind of thing, trying to make things into finite pieces is often a mathematical trick that's used to sort of help the calculation converge in a reasonable way. But then he found that, hey, he was getting the right answer, and that was the reason to keep it. He really didn't understand it. He was a little embarrassed by it because it was a calculational trick, but it did give the right answer, and so he stuck with it and tried to figure out what was going on. Then the other storm cloud, and it's kind of related, was the photoelectric effect. And over in the diagram on the upper right, you see light impinging on a piece of metal. It says sodium metal. And the light, depending on its properties, makes electrons come off, ejects electrons from the surface of the metal. But the funny thing is, that was hard to understand, is that as you change the color of the light, change the wavelength of the light, or the frequency of the light, there's a threshold in the, let's call it frequency, below which you don't get any electrons, and above which you do get electrons. And that contradicted the expectation that the threshold would be not in the frequency, but in the intensity. The idea, logically, intuitively, is that if you increase the intensity of the light, you're likely to get more electrons off. But below a certain frequency, no matter how intense the light was, no electron came off, and it wasn't behaving the way you expected. Above a certain frequency, electrons came off, and if you increase the intensity, well, more electrons came out. So that was something that was sort of understandable. And Einstein, in a paper in 1905, when he published 4 other major papers, by the way, concluded that light was behaving as a particle to some extent, that the light was coming in quanta of energy of a size that was related to the frequency. And following Planck, he said apparently the energy of a piece of light, of a packet of light, is Planck's constant times the frequency. So he's partly building on Planck's work, but with a different kind of experiment, namely using light to push electrons off of the surface of a metal. And later on, considerably later on, 19 years later, he was still ruminating about this, saying there are 2 theories of light, both indispensable, that is a wave-like theory and a particle-like theory. And after 20 years of tremendous effort on the part of theoretical physicists without any logical connection, that is, there still was no theory that really connected the particle nature and the wave nature. The next milestone in 1924, that was about the time that Einstein was saying we don't know what's going on, was the work of Louis de Broglie. De Broglie was a French prince, and it doesn't much matter, but I know how to pronounce his name in Italian. I'm not completely sure in French, so I'm going to pronounce it in Italian, de Broglie. And he thought about this and came up with what now seems like an obvious conclusion, because he was right. He said if light, which was long accepted as a wave, also had particle properties, that's what came out of the calculation of the black body radiation, and also Einstein's interpretation of the photoelectric effect, then maybe matter particles that had long been accepted as particles, why shouldn't they also have wave-like properties? And he suggested that, well, if for light, one of the ways of writing the wavelength was to say that it was that the wavelength written as Planck's constant divided by momentum. For light, that's equivalent to saying that the energy is Planck's constant times the frequency, but another way of writing it is to say wavelength is equal to Planck's constant divided by momentum, and de Broglie proposed that relationship should, I shouldn't try clicking on it, that relationship might hold for all kinds of energy, whether particle-like or wave-like, that the wavelength would be given by Planck's constant divided by the momentum. And let's see, that was his thesis, PhD thesis, written in 1924, and already by 1927, only 3 years later, there was experimental confirmation that electrons, and I've used exactly the same pictures before, except that I changed the incoming energy to electrons rather than light, and the same apparatus gives the same result from two slits. There's a little footnote here. The people who did this, Davison and Germer, these distinguished looking gentlemen here at Bell Laboratories, or what became Bell Laboratories, and G.P. Thompson, who I found an engaging photo of him with his family. And all the other photos I have are rather formal, but I thought this was fun to see that he actually had a family life and, appeared to be a human being like a lot of the rest of us, unlike these people from Bell Laboratories. Did they really do their experiments dressed in three pieces? I don't know. I do know actually that pictures from CERN in the 50s, 60s, 70s, all the pictures of scientists, of physicists, they're all wearing suits. Did they do the experiments dressed in suits? Maybe they did, because that's the only way they were pictured. Okay. An amusing thing here is that this G.P. Thompson was the son of J.J. Thompson, who in 1895 is often credited with discovering the electron. And another way of putting that is that J.J. Thompson in 1895 demonstrated that the electron was a particle, because he looked at it in a cathode ray tube and showed that it could be changed, its direction could be changed, and so on. So his son, in 1927, showed that the electron was a wave, and really the answer was that it was both, and that was a pretty neat result. All right, so things are moving pretty quickly now. If light and matter particles are all waves, is there an equation for the wave? What is the wave equation? That was a challenge put up by a number of physicists, and Erwin Schrödinger in 1925 came up with the answer. He said that he called the wave function psi, Greek letter psi, and he wrote it as h psi equals, and I'm going to read it but not try to explain it, IH over 2 pi, partial derivative of psi with respect to time. So that funny looking backward D is the mathematical symbol for a partial derivative, meaning that you're looking at the rate of change of something with respect to one variable, holding all the other variables constant. And H is referring to an operator. It's related to the total energy of the system. It also involves partial derivatives, and that's about all I'm going to say about it, with apologies. Okay, so the Schrödinger equation, if we accept it, and I told you why you should accept it, it is the, quantum mechanics is the basis of everything in physics, everything in the universe, everything in the world. So it becomes the replacement, the Schrödinger equation becomes the replacement for F equals ma. And if you know the wave function of a system at a particular point in time, the wave function evolves over time, and you can let it go in a deterministic way to determine the wave function at any point in the future. And that's great, but there's an immediate problem, because we're talking about a wave. We're talking about something which may be spread out in space, like this diagram here. We're showing psi as the vertical axis here has some value, x and y as spatial coordinates, and this is something with a peak somewhere, but something that's spread out in space. But the trouble is, and here's an example of a quantum mechanical process, a radioactive nucleus is decaying, sending a particle off in space, and it doesn't give a spread out mush like this. It gives a particle going in a particular direction. So that needs some interpretation. The Schrödinger equation is giving this distribution, but at any given time, if we make a measurement, we find the particle in a definite spot. And so that led to one of the funny businesses about quantum mechanics. And the good people working in Copenhagen, Niels Bohr and Max Born, who didn't actually have an appointment in Copenhagen, but elsewhere in the physical world in Germany, said, well, okay, what happens is very simple. Yes, the wave function is all spread out, and it's giving us probabilities for where we're going to find the particle. But when you look, you find the particle at a particular point, say where that spike is over on the right-hand diagram, and all we have to do is say that the wave function that was spread out collapses to the point where we make the observation, and it's as simple as that. It collapses, the particles in a particular position, and then you use that as the beginning for a new Schrödinger equation with a new wave function that goes on and evolves over time. So the wave function squared, spread out as it was, gives the probability for finding the particle at that point. And then when you actually look, you know exactly where it is. That's the beginning of a new evolution with the Schrödinger equation. And isn't that simple? Doesn't that all make sense? Well, most people would say no. Einstein never thought it made sense. Schrödinger never thought it made sense. That's really damning. Nevertheless, if you go to a textbook about quantum mechanics today, in any university you care to choose, this is what it will tell you. That when you make an observation, the wave function collapses and it goes on evolving from there. We're not really doing any better 100 years later. So quantum mechanics in spades is not deterministic. The wave function evolves in a deterministic way, but then you look and say, where is the particle? And it just changes instantaneously. Because you looked. Does that make any sense? Because you looked. That's the answer. I mentioned I show a picture of it was the 5th Solvay conference. A Belgian industrialist named Solvay started with his money getting physicists together to talk about the issues of the day. And by the time of the 5th Solvay conference, this question of what's really going on with quantum mechanics was a big issue. And so that was a lot of what was discussed. I won't try to point these things, everybody out, but all the luminaries of the day. By the way, you couldn't sign up for this conference. It was by invitation only. You already had to be someone. So there's Einstein. There's Dirac, whom I haven't mentioned. Where was Bohr? He was down here. Well, I know he's here, but then, so yeah. Anyway, you found him even if I can't. So this was the discussion, and this was actually the place where the Copenhagen interpretation began to gel. I'm sure that Born and Bohr came into the conference with a pretty good idea of a point of view they wanted to push, but by the end of the conference, it had pretty much been accepted by everybody. And I'll give a little editorial here. Crazy as it was, all those incredibly bright people said, yeah, the wave function just collapses. What, you can argue with that? How come? Okay, so the Schrödinger equation is a wave equation. It has wave solutions. In free space, the solution is a sine wave. It's taken to apply to both light and matter. In classical physics, the energy density is proportional to the square of the amplitude in a classical wave. Schrödinger proposed that the charge density would be proportional to the square of the wave function, going by analogy with classical physics. Born modified that a little bit and said, this is what's accepted now. The probability of finding the particle not necessarily the charge density, is proportional to the square of the wave function. So the wave function gives you a spread out mush, but it's telling you the probability for finding the particle in any given position. So a bunch of new and unexpected phenomena come with quantum mechanics and Schrödinger's equation, one of which is Heisenberg's uncertainty principle, and he said, he derived, that it is not possible to measure or predict the position and the momentum of a particle simultaneously to arbitrary precision. In classical physics, only the ability to measure would interfere with your ability to make that measurement to arbitrary precision. Quantum mechanics doesn't allow you to do that, and it gives you a limit, a mathematical limit, on how well you can do it. The uncertainty, I'm using the Greek letter sigma, the uncertainty in the x position, using that as an indication for all spatial coordinates, times the uncertainty in the momentum, or the x component of the momentum, multiplied together, has to be at least Planck's constant divided by 4 pi. So, and this is a consequence of basing all this on waves. So here's a look at what the wave function might look like if you know exactly where it is, or almost exactly where it is. So if you know it's right here, so here, and I'm trying to point with my pointer here, which you can't see, but over on the left, if you know exactly where it is, then you get a spike like that for a wave function, and it's very narrow. If, going to the middle diagram, you know precisely the momentum, that means you know precisely the wavelength, and although I've only drawn a few wavelengths there, it goes on forever. That's the nature of knowing precisely the momentum. You get something that goes on forever as a sine wave, and because it goes on forever, you can measure the distance between peaks of the wavelength with arbitrary precision. You know the wavelength, but because it's spread out over all of space, you have no idea where it is. So this is an indication of one limiting case of the uncertainty principle. If you get something mixed, where you know a little bit about where it is, like the more compressed wave function over on the right, it's not just a sine wave, it's maybe scrunched a little bit, but you can determine the wavelength reasonably well, but you can also determine the, that's the momentum, you can determine the wavelength reasonably well. You can also determine the position reasonably well, because it's only spread out a little bit. So that's a place where you're sort of trading off knowledge of the energy of the momentum versus knowledge of the position. So that's one thing that developed You can't measure things, can't predict things with infinite precision. Another neat thing is the phenomenon of entanglement. So in classical physics, each particle can be described by a separate state, which tells you the position and momentum of each of the particles, and that evolves separately from all of the other particles. But in quantum mechanics, there's just one wave function that describes the whole state, all of the particles, no matter how many there are. In fact, potentially there's only one wave function for the whole universe. We usually don't have to deal with something that tries to describe the whole universe at once, but any system that we prepare with multiple particles can be described by one wave function and will continue to be described by that same wave function. That leads to this phenomenon of entanglement. Oh, I see what I did. I said with wave functions for multiple particles, but no, only one wave function for multiple particles. One thing to mention at this time is that the conservation laws that we depend on for classical physics still hold. So conservation of energy is fundamental to physics. We still believe in that. Conservation of momentum. When some interaction takes place, the incoming momentum is equal to the momentum of the particles going out. True of angular momentum, things that talk about the orbital motion or a particle that's spinning. Electric charge has a conservation law. You have to have the same number of plus charges minus negative charges at the end. And there are a few others, but that sets us up to talk about entanglement. So a Higgs boson, just to take an example, has zero spin, and spin is a property of elementary particles that is sort of an intrinsic angular momentum. We don't actually think these things are spinning, but they seem to have angular momentum attached to them. So it has zero spin, zero angular momentum, but it can decay into two electrons. Actually, they have to be an electron and a positron, so the charge balances. Since the Higgs has zero spin, the two electrons have to be spinning in opposite directions. So you can get either one spin is rotating in that direction, and I'm using a common rule of thumb, literally, to say that if it's spinning in that direction, we let the spin vector point up. If it's spinning in the other direction, the spin vector points down. So it may be either that particle 1 has a spin pointing up, as over on the left there, and particle 2 is pointing down, conserving angular momentum, or particle 1 is pointing down, particle 2 is pointing up. But all of that constitutes the wave function, and we don't know which is which. It's not a separate wave function for each particle. It's not that particle 1 may be either up or down, and particle 2 may be either up or down. No, it's one wave function with particle 1 up and particle 2 down, or in the same wave function, particle 1 down and particle 2 up. So we say that the two parts of the wave function are superimposed, and that the characteristics of the two particles are entangled. And so I'll use this, try to go to the extreme where the two particles coming out from the Higgs boson are spread across the whole universe, and I have a picture of starry skies that may be very large distances. So here's the Higgs decaying, decays into particle 1, which I'm showing as an electron, and particle 2, which is a positron. Either one can be either spin up or spin down. And the neat thing is that if they're incredibly far apart, light years apart, but were prepared in the way that we talked about with the Higgs particle decaying, if I measure this one over here and I find it spin up, I can instantly predict that when this is measured over here, it will have to be spin down. It may take a while to get over there and make the measurement. Or maybe I have someone stationed there to make the measurement, but it will take a while for that person and me over here to confer and figure out what we measured. But when the results come out, it will turn out that if I make this measurement here, I measured that the particle was spin up, and therefore I said, aha, the other one has to be spin down. That will turn out to be correct. And the particles are entangled, and when you find out what's happening way over on one side of the universe, you instantly know what's happening over on the other side of the universe. Now it seems like some information is being transferred. I made the measurement here. I'm still trying to point on my screen. Let's say over on the right. And as soon as I make the measurement, I know what the result will be if the measurement's way over there on the left. But no signal is being sent there. It was all one wave function to begin with. The wave function had the two possibilities superimposed. Once I make a measurement and, you've heard this before, the wave function collapses, then I know what's happening over on the other end. It's not a matter of sending information over there. It's still true that information can't move faster than the speed of light. But as soon as I make the one measurement, the wave function collapses, and I know what the result is. Hundreds of light years away, amazingly. And that's where Einstein started saying spooky accident at a distance, and that's why it's appropriate for only a week or so before Halloween. So I'll say that, well, we can't do things hundreds of light years apart. The idea that you can measure things that are superposed over long distances, superposed so far apart that the measurements are made over a distance where you cannot send a signal by light to say, here's what I measured. That's been determined to be correct, measured to be correct. It's experimentally a fact that that spooky action at a distance is absolutely true, and therefore we shouldn't consider it spooky anymore. Checking it all out can still only be done by slow means, which means signals that go at or less than the speed of light. Going the wrong way. Okay, so both Einstein and Schrödinger, who had a lot to do with the beginning of quantum theory, had doubts about the way the theory had developed. And I'll just quote Schrödinger to say, at the Solvay conference where I just showed the picture, he said there, and Heisenberg was taking notes. Schrödinger may not have done that. He said he didn't like the probability aspect of quantum mechanics. He also didn't like the business of spooky action at a distance. So he said, if all this damn quantum jumping were really here to stay, I should be sorry I ever got involved with quantum theory. Nevertheless, as someone has pointed out recently, he didn't turn in his Nobel Prize. Even though he may have not liked all the consequences that came out of the equation that got him the Nobel Prize. There was this famous example that Schrödinger, with Einstein's help, dreamed up to prove that quantum mechanics was incomplete. And one of the issues was always, okay, all that stuff is going on at very, very tiny atomic level distances. Can quantum mechanics ever have an impact on normal life? And so here's what Schrödinger came up with. Let's cook up something where we put a macroscopic cat in a box, and we rig up something where a radioactive source, which follows the rules of quantum mechanics, sends a particle out, but not very often, every so often. You don't know when it's going to happen. But if it actually sends a particle out in its decay, it's picked up by a detector. The detector actuates a relay or something that opens a box that puts some gas into the box. Now, Schrödinger, for whom this was only a thought experiment after all, made this box contain poison, and if this happened, then the cat would die. Sean Carroll, and I took this diagram from him, in talking about this more recently, and being someone who I guess thought fairly favorably about cats, said this will be a gas that just puts the cat to sleep. We're not going to kill the cat, but we can have a difference in state. The cat will be either awake or asleep. So the cat is described quantum mechanically by being in superimposed states. It's superimposed either that it's awake, I'll be kind, or that it's asleep. And both of those are superimposed. Both are true in a sense, in that they're part of the quantum state until I open the box and have a look inside. And I haven't opened the box yet, so we'll wait and see how that looks. Later in life, Schrödinger's daughter said, I think my father just didn't like cats. I think that was after the Schrödinger father had passed away, and people came to the daughter to find out what he really meant by all this. So she quipped at some point, I think he just didn't like cats. Okay, so quantum mechanics works everywhere for everything as far as we know. I've made this illustration and taking a picture that I've showed at a talk here before, that if we take all the fundamental particles that we know of, making up the standard model of particle physics, quarks and leptons over on the left side, which make up matter particles, the particles of force over on the right side, and in the middle, sometimes called one particle to rule them all, the Higgs boson. Every one of those particles is described by quantum mechanics. Now, one thing that's not listed there is dark matter. And what about dark matter? Well, here's where we kind of punt. We think dark matter is made up of particles, but we don't know. And we think of as particles that it must be described by quantum theory. Why? Because everything else is. That's not a terribly good reason, but it's what we had to go on at the moment. It's assumed that dark matter is governed by quantum mechanics. So interpretation, I'm kind of running out of time here, but I'll try to be brief and to say that what was called the Copenhagen interpretation, did I use that word before? I might have. The Copenhagen interpretation of what happens when you make a measurement in quantum mechanics is one of those. It's the one that's really accepted and used every day when we make calculations in quantum mechanics. That's the kind of thing that we want to do better than. All right, you have a wave function that says the particle can be anywhere in a broad range with a certain range of probabilities. You make a measurement somehow, and you find that it's right there, and poof, the wave function collapses. It's neat. And then you go on calculating from there, and it works. You get the right answer. You make a measurement, you make an experiment, and you get the right answer, and the prediction is right, and it's amazing, but it was kind of a piece of magic. The wave function collapses, and you just have to accept it. Or you have to think of something better. Einstein thought generally of a class of interpretations that we now call hidden variables. He thought there were things going on that we didn't know about in the theory, and that really particle 1 had spin up from the beginning. We just didn't know enough, and therefore particle 2 had spin down from the beginning. That was okay, except that this gentleman, who happened to work at CERN, John Stuart Bell, had a day job doing theory at CERN, but he was bothered by interpretations of quantum mechanics, and he spent his evenings toiling away trying to think up better ways of understanding quantum mechanics. And in particular, he began to think that if there are hidden variables, maybe there are differences where hidden variables could give a different answer for certain experiments than quantum mechanics would. And so he came up with things called Bell's inequalities. He had a number of different versions of them. But for instance, a particular version gave a correlation in measurements where you get 2, or 2 times the square root of 2, roughly 2.8 for quantum mechanics, or that correlation less than 2 in the hidden variables theory. The experiment, and so they're fairly different, and you ought to be able to tell the difference. The experimental result agreed with quantum mechanics, and therefore ruled out anything where you try to invoke hidden variables. So that says basically there's no way out. You have to accept quantum mechanics. You have to, well, you sort of have to accept the Copenhagen interpretation. De Broglie himself, and later in the 50s, in the 1950s, Bohm, had a hidden variables theory that they thought of as pilot waves, but they did it in a way that was non-local and non-deterministic. So it turned out that it evaded Bell's theorem, saying that you couldn't have hidden variables. You could have hidden variables in the way that they did it. And so it's possible that this is what's going on, but there's the problem that, and I think it's kind of a fatal disadvantage, that it's difficult or impossible to turn it into a quantum field theory. And most of the successes that I've quoted for quantum mechanics, namely that it works for electromagnetism, that it works for all those elementary particles, come from quantum field versions of quantum mechanics, which I haven't otherwise dealt with, and that would make it very difficult to make use of this pilot wave version. So we have to kind of either do a little better than that or toss it out. And I'm going to mention one other, I'm sorry, it's well after 8, but I'm going to mention this many worlds interpretation, which is kind of intriguing and has attracted a certain amount of attention recently. Hugh Everett wrote a thesis at Princeton in 1957, and his solution was very simple. He said, don't add any extra things like wave function collapse. Just believe in the wave function. Let the wave function evolve, and you will see that at the end, when someone may have made a measurement, it separates into different parts, 2 different parts, where on the one hand, the measurement's gone one way, and the observer is there with the measurement, having observed that. And on the other hand, the measurement went the other way, and you have an observer there, and that part of the equation, and those 2 really don't communicate, but they evolve independently, sort of like separate worlds. And they really have no connection with each other. So one possibility is to say that you've just turned this into 2 worlds, one in which the spin was up, and the other of which the spin was down. So it separates anyway into mutually unobservable portions. And here's, this is actually Sean Carroll's drawing of how this might look as you have multiple points of observation, of measurement, and therefore branching. And it gets worse and worse as time goes on, and you get more and more branches, but okay, why not? How can we prove it's not right? We can't. This may actually be a viable way of understanding and interpretation of quantum mechanics. Hugh Everett in 1957 had a bright idea. How did the field thank him? In the obvious way. It kicked him out of the field. He did go on and had a career with a defense contractor, and eventually formed his own defense contractor. So I think he did okay, but he wasn't really welcome in quantum mechanics anymore because he didn't adhere to the cut and dry Copenhagen interpretation. And that's been the way, by the way, pretty much from the beginning. People who wanted to go in and understand the underpinnings, we just assume you didn't come around to our conferences anymore. Thank you very much. And it's not a very nice way of treating these people, and they were doing good work. It's important. We do need to understand these things eventually. And so we've come back to this a bit in the 21st century. Okay, I used this list that I got out of Wikipedia of each one of which is a class of interpretations. Let's see, did I, yeah, so that first bullet I wanted to quote, David Merman, who's a condensed matter theorist, has also tried to work on the underpinnings of quantum mechanics. His comment was, no interpretations appear every year, none ever disappear. So there are hundreds now, but only a few of which are really much attention is paid for. Okay, so I'll finish with a summary, which I won't actually read through, but if you want to, you can look that over and remember, I hope, the major points that I made, starting from a time when everything was understood in roughly 1900 to a time when things seemed very uncertain and unstable, starting in 1905. And we really haven't gotten over that completely yet. So, nevertheless, even with its spooky aspects, quantum mechanics works perfectly for all the calculations we need to make. We just need to understand what's going on underneath, and hopefully we'll get at that before, let's say, before another 100 years passes. So, thank you very much. Questions? Sorry, I think you got pointed to.
I'm having a little trouble grasping the concept that all matter is a wave, and all waves are particles, and applying that to me as a person. And so I don't understand about a wave or a particle, or a collection of waves and a collection of particles. And maybe you can help take it from this very tiny level of quantum mechanics, put it in.
Well, it's not going to help much, but the only real answer I can give to your implicit question, which is, are you a wave or a particle? The answer is yes. Yes, you are. And clearly there are ways to make it complicated. You are, I assert, made up of zillions of particles. Each one of them is a quantum mechanical object that is both a wave and a particle. But I can treat the object that is yourself as something. What am I trying to say? As an object not made up of other particles. And yes, you have particle-like properties. You go barreling through space and time, running into things if you must, and having interactions with them. But following the the laws of quantum mechanics, as I've at least mentioned them here, you would have a wavelength. It would be incredibly tiny, and it wouldn't have much to do with the way your motion developed, because it would be so tiny. And in almost all ways, your motion would act particle-like, but nevertheless, you would have wave-like properties, but with a very tiny wavelength. Let's see, probably there was more to your question. Do you want to ask another part of it?
Yeah, I have another question, but that was that question.
Okay, well, were there other questions, or, yes, Dr. Back.
I'm going to stand up. I was reminded of something my professor at college, Dr. Richard Still at the University of Nevada, probably 1962 or something like that. We wrote on the blackboard our lecture, I think lecture of dynamics, maybe it was Jackson.
Probably did.
Yeah, right. Anyway, in 1895, J.J. Thomson invented the electron. And I thought that, well, I remembered that. That's probably the only thing I remember from my whole undergraduate year. But let me ask you, Larry, if you can respond to the speculation that basically all of these things, the particles in the standard model and everything else, they're all invented by physicists.
Well, and I actually put that same sentence in just a slightly different way back in my talk. I said J.J. Thomson discovered the electron. So Thomson measured something coming out of radioactive decay. That's where all particles came from in those days. It was called a beta particle. Beta particles, he determined, had a constant ratio of charge divided by mass. And that was the best he could do to say it acts like a particle. He basically bent its path in a magnetic field, and bent it with an electric field. So he bent it one way with a magnetic field and the other direction with an electric field. And that allowed you to measure the ratio of charge to mass, and they all came out the same within experimental limits. So he said, boy, it looks like a particle to me. And he talked about it as a particle. It started as a particle. Radioactivity produced alpha particles, which we now call helium nuclei, beta particles, which we now call electrons, and gamma particles, which we now call photons. And so these were beta particles, and they're already called a particle, but they all have the same ratio of charge to mass. So, was there a question in there? Am I supposed to say? Oh, were they all invented? Were they all invented? No, they were all discovered. I always worry when another PhD physicist shows up in my talk. I believe in the reality of these particles. I know that there's a possibility that new experiments will cause them to be interpreted in different ways. But I think there is an underlying reality, and therefore I'm going to use the word discovered.
Okay.
They were discovered. So a question in the back, there may be more than one. But yes, no, yes, that's what.
How does string theory fit into this?
How does string theory fit into this? Why didn't I talk about string theory? Well, that would have taken me 5 or 6 or 10 or 100 more lectures. String theory is a quantum theory, and it differs because whereas all of the quantum theories that I've alluded to so far treat particles as points and develop quantum mechanics around that, string theory tries to make things more calculable by saying the fundamental unit of nature is not a point, it's a tiny little string, something that has an extension, and these are tiny, very, very tiny. I can't even show you how tiny it is. But it's something that has an extension in one dimension. That's why it's called a string. Extension in one dimension, not two extensions, so it's not flat. It's just a string. And then you develop a quantum theory surrounding that. And a number of interesting things happen because if you tweak it the right way, you begin to see that maybe this part of it could be a theory of gravity, which otherwise we don't have a quantum theory of gravity. This piece of it is already what we understand as electrodynamics. This piece already described quarks. So, but for the present purpose, the simple answer is string theory is a quantum theory. It doesn't contradict my claim that everything we know in nature is described by quantum mechanics. So I think my MC is getting nervous. I should take a listen.
One more question, and then if you're willing, we can address others' questions in person.
And I think you've got your hand up back
Yeah,
there.
I have a question. So I'm a pathologist and a geneticist, and my main interest is in quantum biology. And there's a lot of evidence showing bird migration, entanglement is the reason for bird migration. Smell is a concept you didn't touch on, tunneling. So do you think that quantum biology is something that can be studied above the surface versus everyone studies beneath the surface, all these subatomic particles, controlled environment? Messy world of biology.
I think the name of the game tonight, and always in these lectures, is Stump the Expert. So you're asking a question that's way beyond my understanding of quantum mechanics. I think it's fascinating to think that there could be something like bird migration or smell either in birds or in humans or other animals that relies on intrinsically on quantum properties. Do I think that might be true? I'm just not going to commit myself. It's too dangerous. I'll be quoted years later like Michelson was, saying, do you know what Price said in 2004? He said, there's nothing to do with quantum mechanics and bird migration. And look what we know now. So that would be fascinating, if so, and really why not? Because there are aspects that we don't understand on both sides.
Are we willing to uncover the quantum state of the superposition of the cats just before we
And I'm going to try to make sure that I don't fall on my face as I walk over there. That would be really embarrassing. That's what it would be. And
I'll bring the box over.
I do feel the need to point out while the demonstration is developing that this is sort of a hidden variable construct because somebody knows, not me, but somebody knows how the system was set up and somebody knows the answer. It's not me making the observation. So even though that's what the demonstration is supposed to be. But okay, I'll play along. So, are we ready for a collapsing wave function? There we go. Uh-oh. I'm going to say why this is happening, that collapse is supposed to be instantaneous.
No